If you recall yesterday, we introduced the idea of a line integral. We wanted to set this up as a new thing dealing with our vector fields, but related to an old thing that's just thinking about integrals. Remember that integration is just multiplication, but one of the factors is continuously variable. In the case of a line integral, the multiplication that we have is a dot product because the function that we're integrating is a vector field. The output of our vector field at every point is a vector, not just a scalar. That means we had to adapt our multiplication. The reason that we're using the dot product is because we specifically want to know how much of the vector field is going in the direction of the curve over which we are integrating. In a line integral, we are integrating a vector field over a one-dimensional curve. So the parts that we need are something to describe the vector field, something to describe the set of points that is the curve, and something to describe the direction that the curve is going at all these points. So to that end, we learned how to parameterize a curve. That describes all the points that we're going to be plugging in. We know that derivatives tells us about direction because tangent lines are directions. And we know that the dot product will tell us how much of one vector is going in the direction of the other vector. And these are the pieces that we need to make a line integral. Remember our generic notation for a line integral. Well, first, remember that a line integral, we are integrating a vector field over a one-dimensional curve. We're integrating a vector field over a one-dimensional curve. Our generic notation says the integral over the curve of f dot dr. Remember our integration notation, the integral part of the integral notation, this integral over c. This is all the points that we're going to be plugging into this expression, f dot dr. Then we look at the expression and see what the expression is telling us. F dot dr is how much of f is going in the direction of the curve. So this requires us to parameterize the curve c. Once we parameterize the curve c, we can identify all the points that we're going to be plugging into our expression f dot dr. So now we just have to do that. So to calculate this line integral, we'll integrate the vector field evaluated at all these points. We'll evaluate our vector field at all the points on our parameterization. That is telling us at every point along the curve, the direction of the vector field or the vector from the vector field. Dot product, because we want to know how much of one vector is going in the direction of the other vector. And then we need the dot product with, oops, forgot the important part. Orange is not enough. I need something describing the direction of the curve at all those points, and that's given by the derivative. So I got r prime of t dt is the dr. It's the direction of the curve at any point. Now we need to know what we're plugging in. Notice that our integral dr, where the integral said integrate over the curve C in the direction of the curve, we're not using dr anymore. Once we parameterize the curve, the variable over which we are integrating is t. So this becomes an integral dt. So we just have to figure out what values of t are we plugging in to get all the points on this curve. So our line integral drops down to a nice simple integral from a to b. This is the thinking behind the line integral. We're integrating a vector field f over a one-dimensional curve called C. What we want to know is how much of the vector field is going in the direction of the curve at all the points along the curve. We have to look at our integral notation and read what it tells us. This integral over C says plug in all the points along the curve. This f dot dr is saying how much of the vector field is going in the direction of the curve. And all right, dr, because we know that we're going to be parameterizing the curve C as r of t for t between a and b. That means our line integral can go down to a nice simple integral. Note that although we have a position vector, we're evaluating the vector field at all those points. And over here in green, we're getting a vector from the vector field. Note that r prime of t is also a vector. And when we find the dot product, we end up with a scalar. Because when the dot product is a scalar product. That's telling us the component of f in the direction of the curve. And then since this is an integral, we're just adding up all those values along the curve. It's weird to say it that way because we're adding up over a continuum and there's nowhere to put the plus, but that's what integrals are for. Any questions? Let's do an example with the calculations. Let's set up our vector field. And we're going to start with something simple. I'm going to set up a vector field. That's going to be constant. All the vectors are just going to be pointing in the same direction. I'm going to do 1i, and let's go 1i plus 2j. We need to integrate this around a curve. Excuse me. Let's use everybody's favorite curve, a circle centered at the origin with a radius of 3 for reasons. Now, I can't just say circle of radius 3, because when we have a curve, we need to, when we're going to parameterize a curve, we got to give it some direction. And the direction matters because that's like a big thing going on here with this dot product business. So let's say starting off at 3, 0. And going around once counterclockwise. So in this case, we just described the curve over which we want to integrate. So we'll have to parameterize the curve. But the reason that I picked this circle is because that would not be an impediment. We already know what this parameterization is. So we're like, oh, we recognize this. This is just 3 times cosine ti plus 3 times sine of tj for t from 0 to 2 pi. We have an uncountable infinity of choices for how to parameterize this circle because we have a lot of control. We can choose the parameter that we want. We could set this up so that the integral goes from 0 to 1. Maybe that's one of the things that we want that's important to us. I would have to adjust the period of sine and cosine. So t goes from 0 to 2 pi. I'd want a period of 1. So I'd have to have a coefficient of 2 pi. The 2 pi gets in there somehow. So let's just go with our standard, basic, run-of-the-mill, plain vanilla parameterization of this circle. The pumpkin spice latte in the fall of parameterizations of this circle. Don't get cute with your parameterizations unless you're a computer programmer and you need to build in some job security by making your code indecipherable to everybody else in the world. I'm just kidding. That's ridiculous. I don't know if people do that. Now we've got our vector field that we're going to be integrating. I wrote it in the wrong color, but I'll highlight it in green. This is our vector field. This is the thing that we're integrating. And here, C are all the points that we're going to be integrating over. Now, this is our R of t. I need to find dr. So for dr, I just need r prime of t times dt. So r prime of t, the direction at every point, the derivative of cosine is negative sine, so -3 sine of t I, and the derivative of sine is cosine, plus 3 cosine of t times j. T still goes from 0 to 2 pi. That doesn't affect the direction. Now we can set up our line integral. I've got all the pieces that we need. I've got my vector field. I've got my curve that's been parameterized, and I've got the direction at every point on that parameterized curve. We're ready to plug into our vector, our line integral. So the integral over C of f dot dr instead to plug in all the values of c, I just need to integrate over all the appropriate values of t. So integrate from 0 to 2 pi. Our vector field F is 1i plus 2j. And our direction is -3 sine ti plus 3 cosine tj. dt. We want to know how much of the vector field is going in the direction of our curve. So here in orange is the direction of our curve. The dot product will tell us how much of the vector field is going in that direction. And we're going to do this for all the values from 0 to 2 pi. That will give us all the points going around that circle. That is us plugging in all the values from C. Note that this dot product will give us a scalar. So we start integrating. We still have to integrate from 0 to 2 pi. But we calculate the dot product. 1i times the -3 sine t. So that will be -3 sine t plus 2 times 3 cosine t. So plus 6 cosine of t dt. Notice that there's no more I and j. We calculated a dot product. That's a scalar product. So we just get this scalar function of t. Now we're just back in Calc 1 or Calc 2. We just integrate the function. The integral of negative sine is cosine. So 3 cosine of t. The integral of cosine is sine. So plus 6 sine of t. And then we evaluate this from 0 to 2 pi. Sine of 0 and sine of 2 pi are both 0. Cosine of 0 and cosine of 2 pi, those are both 1. So times 3. Those are both 3. So when we subtract, we get 0. Any questions? How's everybody okay? Yeah. That's a good question. So remember, at every point, we were calculating how much of the vector field was going in the direction of the curve. And so I picked this vector field for to simplify things. So let's take a look at what's going on. So our curve is a circle. So I need to draw a circle. How big do I want to make the circle? Y'all had a professional teacher, then I would have had like the circle pre-drawn and ready to go. But unfortunately, you have me, so a view behind the curtain. I flipped the page and my first thought was, oh yeah, I was supposed to draw a circle there. I even planned leaving this space blank and just did my second class yesterday on the next page. So I did half of a plan. And the big challenge is I didn't bring my circle drawing tool, so it's going to be a sketchy circle. So here's our circle, sitting in XY plane. Cool. Now this circle has a direction. We started off here when t equals 0 at the point 3, 0. And then we went once around counterclockwise, so that at 2 pi we were back at the beginning. At all these points along this circle, we've got vectors telling us the direction of the circle. So when we start off, the circle has a vertical tangent. Up here at the top, we have a horizontal tangent. So at every point, we've got these are the R prime of T's. Also, this is sitting inside of a vector field. And all the vectors in this vector field look the same. So all the vectors in the vector field were 1i plus 2j. So they were all these vectors. There's one of these at every point. I'm not going to draw all of them because I would just have to shade the whole thing green. I didn't have enough space there. There we go. So everywhere, a vector, in particular at all the points along this circle, everywhere, a vector. Everywhere around the circle, we have a tangent. Remember what the dot product tells us. The dot product tells us how much of one vector is going in the direction of the other vector. How much of those green vectors from the vector field are going in the direction of the curve itself. At every point, and then we add up all those values. I know it's weird, it's adding up over a continuum. There's nowhere to put the plus, but we did it anyway. By integrating, we can do that. So this ended up with a total of 0. What could that mean? Let's just think about this in the up and down, in the y direction. For in quadrants 1 and, ooh, I almost said it backwards. Did I say up and down? Let's think about where the curve is going generally up. That would be in quadrants 1 and quadrants 4. So the direction of the curve in quadrants 1 and quadrants 4 is generally up. That whole time, those vectors from the vector field are pushing along the curve. There's a vertical of 2j everywhere along that curve. Sometimes it's pushing not in the direction. Sometimes it's going very much in the direction. At some point in here, they're running parallel. But in quadrants 1 and 4, the vector field is always going in the same vertical direction as the curve. In quadrants 1 and 4, vector field F is same vertical direction as the curve. This is just thinking vertically. It's looking at what's going on vertically. If we flip this over to the other side, take a look at quadrants 2 and 3. Now the vector field is still going in the same direction, still up. And that's working against the curve. The vector field is generally going up, but the curve is going down. It makes sense that vertically, these two sides would cancel out. The symmetry of our curve and the constant nature of our vector field are what causes those two sides to kind of cancel each other out and balance. A similar thing happens in the horizontal direction. So this is just an analysis of the vertical direction. So a similar thing will happen in the horizontal direction because the vector field is constant. If we just think about how much of the vector field is going horizontally, it's just 1 everywhere. So on this top half of our curve, the vector field is pushing against it. The bottom half is just a copy of the top half in the other direction, where the vector field is pushing along. Remember what we want to know. We're imagining the vector field is the water, and this is our path through the water. So horizontally, this first part of the trip, horizontally, is difficult because we're fighting against the current. But the second half, we get that back because we're going with the current. And that happens horizontally and vertically, and the symmetry of our path means those two are going to balance out. So that's why it makes sense that we get a total value of 0. bold claim when the teacher just says, so it makes sense that this happens. And the students are like, oh, dude, that's exactly what we're asking you. It doesn't make sense. Make it make sense. It balances out. The wind is constant. In one direction, I'm riding into the wind, making it difficult. In the other direction, I'm riding with the wind. So all the extra stuff that I had to spend going one direction, I get back when I go the other direction. Let's imagine what would happen if we just restrict to one part of this curve. Let's just grab one part of this curve and see what happens. Let's just consider the curve from t equals 0, same curve, same vector field. Let's restrict the curve just to that quadrant 1 and 2, just from t equals 0 to t equals pi. What do you expect the value to be if we just go from 0 to pi? Let's find out. So I'm just looking at quadrant 1 and quadrant 2. So all the other setup is the same. All this other calculation I get to recycle. It's just that my integral is going from 0 to pi. We're still going to have the same dot product. We're still going to have the same antiderivative. I just need to take 3 cosine t plus 6 sine t from 0 to pi. So my integral over C1 of f dot dr will just be 3 cosine. I turned the page and that made me forget. 3 cosine of t plus 6 sine of t from 0 to pi. Same vector field, same parameterization. We're just changing the parameter, adjusting the parameter to change what our curve is. So here, sine of pi and sine of 0 are both 0. So that's out. Cosine of 0 is 1. Cosine of pi is -1. So 3 cosine of pi is -3. This is 0. Minus 3 cosine of 0 is 1. So -3, oops, plus another 0. Well, I should say -0. I know it doesn't matter, but let's make sure we distribute. So here we get a total value of a total of -6. When we look at what's going on in quadrants 1 and quadrants 2, notice that our direction is generally to the left on our curve, but the direction of our vector field is generally to the right. So it makes sense that we get a negative value for our total, because the vector field is going against our direction. Any questions? So that's an indication that it's taking us, we have to work harder going that direction because we're fighting against the vector field, and that's represented by this negative value. Without calculation, what would be this integral over the bottom half? Integral from pi to 2 pi. What would that value be? Knowing that the total going all the way around was equal to 0 tells us that going in this direction, if I go from pi to 2 pi, that must be giving us a value of 6 because they're going to have to cancel out because we know our total value is 0. Any questions? How's everybody okay? Let's pick a different part of the curve where a similar thing is going to happen. Let's go from t equals pi over 2 to t equals 3 pi over 2. So this is in quadrants 2 and 3. All I'm changing is where the part of the curve that I care about. My vector field is the same. My parameterization is the same. So my direction is the same. So I can just take my antiderivative, 3 cosine of t plus 6 sine of t, and evaluate from pi over 2 to 3 pi over 2. Notice that at the pi over 2 and 3 pi over 2, now cosine doesn't matter, and it's sine that we care about. What's the value going to be? You got 5 seconds. 4, 3, 2, 1. Not quite. What's the vector field? The vector field was 1 in the x direction and 2 in the y direction. Notice that the one that didn't matter here was the 3, and we ended up with a 6. Now the one that doesn't matter, or the one that didn't matter was a 6, 3 mattered, we ended up with 6. So what's going to happen here? Let's find out. So we'll have 3 cosine of 3 pi over 2 plus 6 times the sine of 3 pi over 2 minus 3 cosine pi over 2 plus 6 sine pi over 2. Unfair for me to spring questions on you. Bold answer. Love it. But the value, we're only off by a factor of 2. We can see that the values that don't matter here are cosine. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1, so that's going to be -6, minus 3 times cosine of pi over 2, that's 0, minus sine of pi over 2 is 1, so distribute the negative, -12. This makes sense. When I picked quadrant 2 and quadrant 3, that's where the curve was generally headed only down direction. The reason that it ended up being -12 instead of a -6 is that the vector field is twice as powerful in the y direction. The vector field is 1i plus 2j. So our vector field F is 1i plus 2j. So it makes sense that the amount of work that's going to take, it's going to require to go from the top down to the bottom is going to be twice as much as going from the right to the left. I just brought up the work thing. Your typical framing for line integrals is that work is equal to force times distance. That's when we're not worried about direction. Work is equal to force dot distance. That's our framing that we've been using. Just like in Calc 1, when you start talking about definite integrals, your framing is area is equal to length times width. I like that one a little bit better because it's purely geometric, and it's the only multiplication that we need. Distance is equal to rate times time, so rate is length and time is width. But work is equal to force dot distance. Kind of helps support the narrative of the vector field is the current, the curve is our path through the current. Any questions? I'm sure there are many faults in my analogy with work is equal to force dot distance. But that's because that's a physics thing that I just kind of pilfered from physics to use in my math problems. How's everybody okay? This is the game. We have to be able to parameterize curves. Once we parameterize the curve, that's the hard part. A line integral is just going to drop down to a plain old integral. Look how much integration and derivatives we didn't need to do in this. We just took derivatives of the two components. We had to integrate a function of one variable. Now, the next step is to see what happens if we start changing things around. So here we had a nice constant vector field. So now, what if our vector field isn't constant? So what we have to do is take an example. I want to use the same curve, and I want to alter the vector field so that it has some variables in it, because right now this was pretty easy to set up with our dot product. So let's do an example with a vector field that has some x's and y's in it. It's not going to get too exotic, but we're going to have to figure out what's x and what's y. Then we're going to have to integrate something else. And then we're going to have to think about what the results tell us. Now, if I did that example right now, my vector calculus would be a breeze. I could switch to surface integrals. We could be like all fundamental theorems of calculus, and everything would make perfect sense, but only if I do this example right now, when it's still fresh in your mind. If I allow any amount of time to pass between finishing this example and starting my next example, calculus is going to be the same struggle that you were going to have before. I could just eliminate all that work by doing this example right now. So let's get, oh, look at the time. That's going to do it for today. I will see you all on tomorrow. I guess we're just going to have to do some work. Everybody have a good day, and thanks for playing.